Now, most star-forming nebulae have enough dust and gas that they can make far more than one star. They can make dozens or hundreds or even thousands of stars. These stars all are forming at the same time out of the same cloud of gas, and so we're going to get a bunch of young stars all formed at the same time together in space, and this is what we call a star cluster. The Orion Nebula is in the process of making a new star cluster right now. There are two main types of star clusters that we can see out in space. On the left, we have a picture of one type called an open star cluster. What you can see about open star clusters, there are not a lot of stars. There are definitely more stars in the center than at the edge. On the right here, we have a picture of the other type of star cluster, a globular star cluster. Globular star clusters can have hundreds of thousands of stars, and so they really stand out. They look just like someone poured a bunch of sugar on a portion of the sky. Really gorgeous to look at. Now, open clusters themselves have many flavors. So here are some. You see in the upper left, if an open cluster is just forming, it might still have gas around it. Bottom left, you see that some open clusters do have a lot of stars, although not nearly as many as a globular. And the three open clusters on the right, you see, have varying amounts of stars. Sometimes you have blue stars, sometimes you have red stars, sometimes you barely have any stars at all. But all of these are open clusters. And the main similarity between them is that all the stars are the same age, and there are a few dozen to maybe a few thousand stars at the most. Globular clusters, they all look very similar. They all have hundreds of thousands of stars. They all look like a little ball in space, tightly packed, all these stars really close together. So, whereas open clusters have a wide variety, globular clusters all kind of look the same, which makes us think that they all are formed in the same way. If we look at the Hertzsprung-Russell diagrams for these stars, on the left we have the open cluster, the Pleiades, again just a handful of bright stars. We make a Hertzsprung-Russell diagram and we see bright blue stars, faint red stars, and all the stars in between. So no red giants here, and there's only one white dwarf. It's not even on this plot. On the right we have a globular cluster, and this is a typical globular cluster Hertzsprung-Russell diagram where you see most of the main sequence, especially for the bright blue stars, is not there. We see the main sequence for the cooler, fainter stars, for the low mass stars, and then we see a lot of red giants, and if we looked closer we'd also see a lot of white dwarfs in this star cluster. They're just, again, not plotted on this graph. So why do these Hertzsprung-Russell diagrams look so different for the two different types of star clusters? Well, let's go through the reasoning of both what a star cluster is and how it would make a Hertzsprung-Russell diagram. So it's an observed fact that when a star-forming nebula makes stars, it produces stars of all different masses. If you look at the Orion Nebula, you see some very massive stars, many times the mass of the Sun. You see stars about the mass of the Sun. You see stars much lower mass than the Sun. It's also an observed fact that all star clusters that have a nebula have both hot and bright stars, again these are the massive main sequence stars, and the cool faint low mass main sequence stars. Now if we look at most open clusters, those that do not have nebulae around them, we see that often the brightest, hottest, bluest, most massive stars are missing, and then down below some mass, which can be anywhere, which varies from cluster to cluster. It might be 1 times the mass of the Sun, or 3 times the mass of the Sun, or 5 times the mass of the Sun. Fainter than some limit, we will see all of the stars in the main sequence, but brighter than that limit, more massive than that limit, we don't see the stars. And again, where that limit is varies from cluster to cluster. It's also an observed fact that no globular clusters have stars more massive than 90% the mass of the Sun, 0.9 solar masses. However, they do have stars from 0.9 solar masses all the way down to the least massive stars we know about. We can tie all this together by making a simple hypothesis that more massive stars end their lives more quickly. So that in a star-forming nebula, stars are just being born, so of course you're going to have massive stars. As you go onward in time and look at older and older clusters of stars, low-mass stars will still be there, but high-mass stars have used up all their fuel, they've ended their life, and so we don't see them anymore. And then this also implies that all globular clusters, because they don't have any stars more massive than 90% that of the Sun, and we know the Sun can live for 10 billion years, this implies that all globular clusters are old, and in fact older than 10 billion years. All open clusters are younger than that. Let's summarize the properties of star clusters that we've talked about, and a few that we haven't. Open clusters, they typically have a few dozen stars, maybe a few hundred, occasionally 1,000 or a couple thousand. If we measure their ages, which we'll talk more about in the next couple mini lectures, we get ages of a few million years to a few billion years. Shape, they're irregular in shape, no good shape. We usually find open star clusters in the Milky Way. So if we look on the sky, most every open star cluster is in the band of the Milky Way, with a few exceptions. And if we measure what the composition of these stars are in open clusters, most open clusters have a composition very similar to that of the Sun. 75% hydrogen, 73% helium, and 2% everything else. Now if we then go to globular clusters, well, globular clusters have a lot more stars, 100,000 to millions of stars. Globular clusters are all old. Our best estimates of their ages are that every globular cluster in our galaxy is between 11 and 13 billion years old. We saw that all globular clusters look about the same. They're kind of spherical in shape, circular in shape. The location of globular clusters is typically in the halo of the Milky Way, outside the band of the Milky Way. And if we measure the compositions of stars in globular clusters, we find that they have many fewer heavy elements in the Sun. So they're 75% hydrogen like the Sun, but they're more like 24.5 or 24.9% helium, with just a fraction of a percent of everything else. So in summary, there are huge differences between these two types of star clusters, open star clusters and globular star clusters. Their Hertzsprung-Russell diagrams look different. They have different stars in them, different masses of stars in them. They're located in different places. They have different numbers of stars. They're made out of slightly different compositions. They're really two completely different types of objects. In our next mini lecture, we'll discuss how, despite the fact that they're different, these two types of star clusters allow us to study how stars change over time and provide evidence helping to prove our hypotheses about how stars change over time. So we may now complete the mini lecture response for this mini lecture number 2 and then continue on to number 3, the life cycles of Sun-like stars.